Okay, today new chapter, we did chapter 6. Chapter 6 is more on the isentropic or compressible flow. Okay, so chapter 6. So chapter 6, we look at 4 things: ideal gas, Mach number, isentropic, non-isentropic. So one particular things in final exam is Mach number. So you need to use the equation of Mach number and speed of sound in final exam. Okay, what does compressible flow happen? Compressible flow happen when Mach number more than 0.3. Okay, so remember this magic number. Mach number equal to velocity divided by speed of sound. If this one more than 0.3, then you are having compressible scenario. Okay, unless the question mentioned ignore compressibility effect, then you have to use compressible flow equation. Okay, let's watch one YouTube video. This is what happened if, oops. Okay, so this basically they conduct an experiment by capturing a shock wave of a bullet. So they shoot one bullet from this gun, and then they capture by using a high-speed camera. So they capture. So they capture one. Let me fast forward to, okay. So this is the video that captured by this guy. So as you can see, the bullet is flowing across the camera in a high speed, and they're also showing you what happens if you having a higher speed of bullet. Okay, so this video you can watch is a very long explanation on shock wave. Quite interesting video, so you can see it later. Okay, so basically what happened when you have a compressibility effect means you can see that the air was compressed and you see a shape like this. Okay, this is, we call it shock wave. Okay, first equation, I think you see this one before in thermodynamics class. This is called ideal gas equation or equation of state. Give you rho density, rho equal to P divided by RT. Okay, rho equal to P divided by RT, ideal gas equation. R is a constant, gas constant. R given by lambda or gas constant divided by molecular weight of the gas. Okay, so this one you learned in thermodynamics already, right? And you'll be given this table in final exam. So table 1.7, 1.8. So just be careful using this table. On the top, this one is unit imperial, which we will no longer use. But however, if you go and further study master in United States, then most popularly you need to use the imperial unit. However, if you're in Asian, you go to Singapore, you go to Korea, go to Japan, we are all using unit SI. So use table 1.8 for this chapter. So 1.8 give you temperature, material, density, specific weight, dynamic, kinematic, get constant, and specific heat ratio K. Okay. So I think this one you learned before. What is specific heat at a constant volume, CV? Okay, CV. We look at ideal gas scenario. So in thermodynamics for ideal gas, first parameter we look at is specific heat at constant volume given by the changes of internal energy U divided by temperature. Okay. So if you rewrite the equation or you rearrange the equation, you pull dt to the left-hand side, you get CV dt and small changes of internal energy. So you want to get the total internal energy. What you do, you just add an integration sign both sides. You integrate d something, you get the full numbers or full value of that one. Okay, so integration, you get this form. So u2 minus u1 equal to integration of CV over temperature, T1 and T2. So you arrive at U2 minus U1 means the changes of internal energy equal to CV. CV is a specific heat at constant volume times the change of temperature. Okay, so this tell you how you calculate internal energy using specific heat at constant volume CV. Another one is called enthalpy. Enthalpy. There's another one called entropy. So now we look at enthalpy. Enthalpy H equal to U internal energy plus pressure divided by density. Or this term we call it pressure energy. So enthalpy, look at two dimensions. One is internal energy, one is pressure energy. Internal energy U. How to get U? Just now we derive how you get U. U you calculate by taking CV times the temperature to get U. Okay, so again, look at the table. Okay, this table don't have CV. There's one material table that you can find CV. So the equation you see on your screen here is enthalpy. Enthalpy H equal to U plus pressure divided by density. The next one is specific heat at constant pressure, CP. All right, just now is CV. CV is V is volume. V is constant volume. But if you look at CP, is at constant pressure, specific heat at constant pressure. What does constant pressure link to? Constant pressure link to enthalpy. Okay, is the change of enthalpy divided by temperature. Okay, CP link with enthalpy, H, CP and H, they are good friends. However, CV is good friend with internal energy U. CV always link with U, CP always link with H. So as long as you clear of these two, then you are fine with the rest of the formula. Okay, if you want to find internal energy U, you use CV. If you want to find H, enthalpy, you use CP. Okay, you do the same, rearrange the equation, apply integration both sides, you'll get H2 minus H1 equal to CP changes of temperature. H2 minus H1 equal to CP T2 minus T1. Okay, so this one just a recap of what you learned in thermodynamics, maybe thermodynamics 2, when you learn about enthalpy and internal energy. Okay, just a recap. All right. Now, when you study about ideal gas, I'm not sure your previous lecturer, do he or she tell you how to develop the relationship between constant constant specific heat for volume and pressure, CP and CP. So I'm going to show you on my slides here. So as we know, enthalpy given by this equation, H equal to U plus pressure divided by rho. And we know that rho equal to P divided by RT. This one is from ideal gas. So from these two equations, you know that later we'll substitute this one in here. we will arrive at H equal to U plus RT. Okay, you substitute this rho equal to P divided by RT. You substitute over here, you cancel out the pressure, and you only left out RT. Okay. Cool. It is cool. Have any question? It is all right for you so far?
No.
Cool. Okay.
Yeah.
All right. So this is how you start to derive equation for relationship for CV and CP. You start with enthalpy, followed by definition of ideal gas. You arrive H equal to U plus RT. H is enthalpy, U is internal energy. Okay. Then you differentiate. Differentiate means you find a very small changes inside there. You know that H can change, U can change, R is the constant value, cannot change, so you cannot differentiate it, but temperature can change. So you modify the equation above, dH equal to du plus R dt. Okay, then recall the relationship of CV. CV always good friend with internal energy U. CV equal to du over dt. Pressure good friend with enthalpy. So Cp equal to dH over dt. And we want to write this equation in terms of CV and Cp. Do you know how to do it? Shirley, if you want to write this equation in CV and Cp, how do you do it?
Just take the equation from CV and CP and then we rearrange it and substitute inside the differentiation equations.
Okay, so how do you, what step you use to change into CV, this equation, Shirley?
You
take
just substitute. dH equals to CV dt plus R dt.
So you are taking the whole equation divided by dt, right? Okay, good. That is what I want try to ask. Okay, you take this equation, you divide the whole equation by dt. Then you will see, you compare these two definitions, then you will get Cp equal to dH over dt on this side. This one will become du over dt. Then you get Cv. This one you cancel, you get R. So you'll get this equation. Then after that, you compare side by side, rewrite as Cp equal to Cv plus R. So this is a relationship between the two constant value of Cp and Cv. Okay. So you move this one to the left, Cp minus Cv equal to R. So gas constant R is actually the differences between Cp minus Cv. So if you're given a table, this table, okay, this table, you see that you're having the R, constant value R. So this R actually is the differences of Cp minus Cv. Okay. So if you're given one value, Cp, you're able to find Cv by looking at this table. Okay. Okay. So this is what we find just now. This is what we find just now. So Cp minus Cv equal to R. And if we define specific heat ratio K as Cp divided by Cv, if we define K equal to Cv divided by Cp divided by Cv, you can write your Cp equal to R K divided by K minus 1. Okay, you substitute Cp and Cv inside here. Okay, you rewrite, let's say you want to put in you want to write Cp. So Cp equal to KCV. You substitute inside here. Okay, I do one substitution for you. You rewrite this one. Cp equal to KCV. Then after that, you substitute inside here. Okay, so you have Cp minus Cv equal to R. So you know that your Cp is equal to KCV minus Cv equal R. So you can factor this one out. Cv equal to K minus 1 equal R. Rearrange this one, you'll get this one. Okay, sorry. Rearrange this one, you get this one. Okay, put K minus 1 to right hand side, you get this one. And then the next one, you rewrite Cv equal to Cp divided by K. Okay, substitute inside here, rearrange, you'll get this one. Right. We'll come to these slides, revision, and your revision, try to understand how you get these two. Because later we will use these two definition to build a further complex equation. So Cp equal to Rk divided by K minus 1, Cv equal to R divided by K minus 1. So by having these two equations, you can find R value in the table, K value in the table, you can find what is Cp, what is Cv. So what table I'm referring to is table 1.8. This one. So once you have your R value, you have your K value, you can find Cv and Cp value by using these two equations. Sorry. By using these two equations. So I just show you how to find value for Cp and Cv. So when you come to final exam, so you will see table 1.8. So you are given the R value, you are given the K value. So you manage to find Cp and Cv. The next one, for compressible flow, entropy S. Entropy S. This is different from enthalpy. Enthalpy is H, entropy is S. Enthalpy is H, entropy is S. Entropy is energy. H also energy, but they are different meaning. So there is an equation here. If you take d ds T ds equal to du plus pressure times the changes of 1 over density, d over 1 over d, differentiate, right? Small changes of 1 over density. So T here, we use absolute temperature, entropy, and so on. So we'll differentiate, we'll get H equal to U plus P divided by rho. Okay. And so on. Okay. So you take this one, you differentiate the equation, you differentiate H, you get the H, differentiate internal energy, you get the U. However, this one is a fraction number. You will get P when you differentiate a fraction number. You get PD, the nominator, plus the nominator dP. Okay. You need to recall differentiation skill. This one, where you differentiate, you get two entity because you have a fraction number here. Okay, so if you compare side by side these two equations, you take the top one minus the below one, you'll get what is TS. TS equal to dH minus 1 over rho dP. Okay, you take the top one minus the bottom one. So this one will cancel. This one will become negative because this equation minus this one. So TdS dDH, but you move to the left, you get positive dH. And then PdP, PD rho minus PD rho. So you only left out this one. So you only left out this one, and this one. So you arrive at the equation on the left-hand side. Then recall ideal gas equation again. Rho equal to P divided by RT. And definition of CV. So you can write this equation in terms of CV. So as you can see on the right-hand side. So ds equal to CV dt temperature over T plus R divided by 1 over rho density d 1 over rho. So basically we are still at mathematics stage. So we are assuming CV as a constant, this one, CV as a constant. So when you have CV as a constant and you integrate both sides, you'll get S2 minus S1, CV ln, because this is 1 over something. You get a ln when you integrate it. T2 minus T2 divided by T1 plus R ln density 1 and density 2. So just take note on this one. Normally, student, they will write this one as 2. They will write this one as 1. So take note on this screen that the notation or the subnote of the number here is a bit different. So if you're using CV, S2 minus S1, the temperature is 2 divided by 1, density is 1 divided by 2. Density is 1 divided by 2. Okay, later you see when you change this one to CP, the notation number will be different. Just be careful when you use the CV and CP. Okay, I'll show you another one. So you use the same equation and you apply CP definition in here. And you do the same process. You'll get S2 minus S1 equal to CP ln T2 minus T1, and you see minus R ln pressure 2 divided by pressure 1. So it's a bit different from the previous one. So the previous one, if you're using CV, it is temperature and density. This is density, not pressure. If you're using CP, to calculate entropy S. So you're using temperature and density. However, if you use CP to calculate the entropy, you are using temperature and pressure. Okay, just take note on this one. So this is a very important equation when you want to calculate entropy using CV and CP. All right. So these are the two important equations when you want to find the changes of entropy. S2 minus S1. There are two ways to calculate. One is using CV, one is using CP. Okay, if you're using CP, you use temperature and density. If you use CP, you use temperature and pressure. One is positive, one is negative. Just take note on that. One is positive, one is negative. And the parameter you use is different. Just take note on this one. These are very important slides. Okay. Okay, the next one, I'll go very fast. The next one is a second law of thermodynamics. What happened? They happen in adiabatic and no friction flow or frictionless flow. What happened? So we have covered what is these two already. The differences is one is CV, one is CP, but both are calculating entropy. So you've seen these two equations before that we showed you just now. CV, CP, CV temperature and density, CP temperature and pressure. So when you have adiabatic scenario, both entropy S2 minus S1 is 0. Okay, just take note on this one. So when you see this one in the exam question, adiabatic means your entropy, the changes of S equal to 0. So it depends whether you're having density or not, whether you're having temperature or not, or you're having pressure or not. So depending on what you have in the question, you decide whether you want to use CV or CP. How to find the CV and CP value? I did show you by using the R and K just now to find CP and CV. Okay, this one, table 1.8. Okay, so basically, you just substitution of numbers only. Okay. What else? So if you have an isentropic flow, then this one will equal to this one. Meaning, the one that you are using CV will equal to the equation using CP. Yeah. So if you have an isentropic flow, what mean by IS isentropic flow means you have the same entropy, entropic S means the S is the same, will be same. And isentropic with adiabatic scenario happening the same time, then both isentropic will be 0. Okay, sorry, changes of entropy will be the same. If you have an isentropic with adiabatic flow, then you can equal the equation of both sides equal 0. Yeah, so this is also another important slides. Okay. So when you have a constant entropy flow, what I mean by constant entropy? What is entropy S? When your S is constant, another name for it, we call it isentropic flow. So when the S is constant, the delta S, or if you take S2 minus S1 will always 0. There's no changes of isentropy. No changes in entropy. Okay, so this equation I showed you just now, the CV component was same as CP component. All right, again, CV linked with temperature and density, CP linked with temperature and pressure. Okay. Then recall, we try to rewrite the equation above in terms of R and K. We don't want to see Cp anymore, or we don't want to see Cv anymore. What happened to the equation above? You will get the ratio of temperature, density, and pressure. Okay, so when you substitute this one here, you substitute this one over here, you do the rearrangement of equation, you'll get this very important ratio for ideal gas aerodynamics, thermodynamics. You'll get T2 minus T2 divided by T1 equal to with the exponential or with the power of K divided by K minus 1 equal to density power K equal to pressure. This is 1. Above there, if there's nothing, then this is 1. So as you can see, there's an equivalent between temperature, density, and pressure. This one happened at ideal gas scenario. And this one only, this ratio only can use when the question state you're having an isentropic flow, because you are deriving from this equation, isentropic flow, it means delta S equals 0. Then only you can use this ratio. Okay. So if you rewrite the equation, another equation you derive from above, pressure divided by density with the K, you get a constant value. Okay, you get a constant value. But what is important to memorize, or when you try to solve ideal gas isentropic flow, the middle equation will help you to solve almost 80% of the question. Okay, so this one you put it somewhere. This is a very important equation when you try to solve ideal gas thermodynamic question. All right, so we will come back to this tutorial question after a short break. Okay, let me stop the recording.